Hey folks, Dr. G here, and today we're going to do an introductory lesson on running molecular dynamics simulations using the ChemCompute web interface, and then using the Python library MDAnalysis to analyze the results we get. Since I already have a lesson on using Jupyter Notebooks, I'm going to assume that you already know how to use a Jupyter Notebook, but if not, I have a video for that and I will link to that. All right, let's get into it. So taking a look at this Jupyter Notebook, there's some instructions in the beginning. Of course, the link to the video will go here. I can't put that there yet because I'm currently filming it, right? And the next thing we have is installing libraries. So when you install Python, I usually encourage my students just install the Anaconda distribution of Python so that you get a whole bunch of libraries all at once. But as you progress as a coder in Python, at some point, you're going to find a library that you want to use that you don't yet have. And so these are commands for installing some libraries that we'll need for this exercise that you probably do not yet have installed on your computer. And the reason why I give them to you commented out initially is because this is the sort of thing that you run once, right? When you use a library, you import it right here, right? But then here, this is where you install it. So it's like, every time you create a new Word document, you don't reinstall Microsoft Word or something like that, right? You just use it. That's like importing it as just using. But if your computer doesn't have Microsoft Word, that's when you install it. So this is the installation process. So there are two libraries we're going to be using today, MDAnalysis and NGLview. So MDAnalysis, as you might guess, is for analyzing molecular dynamics simulations. And NGLview is a really great library for doing molecular visualizations. So if you've used things like Chimera or VMD to analyze molecular data, it's a bit like that, except you can do it right inside a Jupyter Notebook, which is really cool. You might notice that I also have this install ipywidgets. Well, the first time I did the installation on my computer, I found that NGLview did not have something it needed from ipywidgets, right? Libraries, they use each other, right? So that we call these dependencies. The library needs to call some function from a different library, whatever. And there was something up with my computer that there was something in ipywidgets that was not updated that NGLview needed. And so I got this error message and it mentioned ipywidgets. So I thought, let me just try updating ipywidgets. And sure enough, that did the trick. So that's why I put that there, just in case you need to do the same thing. All right, so once everything is installed, you can run this cell here and import all of the libraries we'll be using today. In fact, if you're not sure whether these are installed, just try running this. And if you get an error, it says it never heard of a library or something like that, then you know you need to install it. So that's one way to know. So if you're taking the class with me, I probably assigned you a specific molecule to use, and I probably told you which molecule to use by telling you its PDB ID. So that's Protein Data Bank Identification. All right, so the protein that I'll be using today is 1-CSP. So if I Google that, I'll just type 1-CSP PDB, and sure enough, there it is. So RCSB, right, this is the organization that does this. This is the structure. So this is the protein that I'll be working with today. So what I'm going to do next, I'm going to download the PDB file. So if I download, and then there's all sorts of different formats you can choose. Just select PDB format, and now this is in my downloads. So once your PDB structure is downloaded, just go into your downloads folder and make sure that you drag it into the directory where you're working, okay? So, quick note, I often find with my students who are new to this type of work, new to programming, that they're not really sure where their files are being saved on their computer. They haven't been organizing their things into folders, right? So let's talk about folders for one moment. So on my desktop here, I have this ChemCompute MDAnalysis folder. I created that just for the video I'm doing today. And if I open that up, ChemCompute example, right? Here's the files that I'll be using. Right, so this is the file that you'll download from my GitHub page. So put that somewhere that you know exactly where it is on your computer. So here it is. This is how I get to it, right? My directory path to get there is I go from the desktop to here, and I'm there, right? So I know where it is. So then when you download your PDB file, make sure it's right here, same folder, right? There's that, there's that. They're both in the same place. This is really important. All right, so getting back to our analysis now. The first thing we want to do is we want to load our structure. So instead of your.pdb, let's put the name of it. So it's 1-CSP. I have a few extra files in here, just pay no mind to them. put that there, load it. Okay, that worked. So what have I done here? Well, so when I loaded the library, I said import MDAnalysis as MDA. So I just have to type out MDA. I don't have to type all this out every time. So I say MDA.universe with a capital U. Universe is an object inside of MDAnalysis that's super useful. You can store all kinds of molecular data in that. It can recognize different typical file types like PDBs, PSFs. There's different files that are associated with molecular dynamics simulations, and this object knows how to deal with all of them. So it's pretty awesome. So when I loaded this in here, right, it was able to read this file because it was in the same directory. If I move that somewhere else, this is going to fail. Okay. So after we've done this, let's take a look at our molecule. If we go view, so I'm going to create an object called view, and view is coming from here, right? NGLview. And I gave it a little nickname again, right? So NV, all I have to do is type NV and it's NGLview. So nv.show MDAnalysis. So basically, show MDAnalysis knows that it's going to get an MDAnalysis universe. I'm basically telling it like, hey, I'm going to give you a universe from the MDAnalysis package. So these two can work together, which is amazing, right? We don't want to take this stuff for granted. Anyway, so we have this object here. It's a universe. We pass the universe to show MDAnalysis and then store the resulting object as view. So our variable view, if we just put view in a cell and execute it, watch what happens. It shows us the view. I think this is just so cool that we could do this right inside of a Jupyter Notebook. I love this. So now we can take a look at our molecule inside of a Jupyter Notebook, right? If I left click on it and drag it around, I can move it. I can zoom in by using like the wheel on the mouse, or there's commands you can do with a touchpad, right? If I do 2 fingers, drag, it zooms in, 2 fingers. If I click down hard with 2 fingers, I can actually move it around. If you click with 1 finger, that rotates it. So you can get a look at what this protein looks like. All right, so now the first thing we want to do, we want to get an idea of how big this protein is. And why is that? Well, we're going to do a molecular dynamics simulation of this protein using MDAnalysis. And if you're going to simulate a protein, you'd better put it in water, right? Because water is the solvent of life. So if you want to see how a protein moves in a way that's relevant to life, it needs to be simulated in an environment of water. And so how do we do this? There's different ways to do it, but we're actually going to use ChemCompute has an interface that will build a water box for us. So it'll simulate individual water molecules and it'll put them in a box around our protein. But we need to tell it how big our box needs to be. And so to do that, we need to know how big the protein is. All right, for this one, I gave you a big hint. So if we copy this here and we paste that there, this is a command here. So we said min chords. So U1, that's the universe we just created, right? We created that universe. And the universe has different things we can call from it. So let's break it down a little bit. If I comment that part out and then output min chords, we see that there's some sort of object that has 545 atoms. Okay, well, great. We know how many atoms there are now. Now, what if we look at the positions? Now let's comment it out from here over. Okay, so this is an array with 3 numbers. What do you think that is? 3 numbers for positions, X, Y, and Z, right? So we've got our positions of our atoms here. And if we look at the data type here, this is a numpy array. Okay, so there's a lot of things we can do with arrays. And one thing that you can do with an array, right, a built-in method for numpy arrays is the min function. So then that's where min comes in. So if we run min, we get this. And notice too, we have this parameter axis equals 0, right? So there it is. So if I say axis equals 1, let's compare the two. I think this is the easiest way to explain the difference. There's axis equals 1. There's a whole bunch of these, right? For axis equals 0, it's just the 3, right? And just to remind you, here's what it looks like before we take them in, right? This is the shape of this thing. In fact, we could just get the shape. I could say dot shape. And we see that it's 545 by 3. So there's 545 rows and 3 columns. So given that shape, think about what axis does now. right? So axis equals 0 means if I go down the column, the x column, and I say, okay, what's the smallest value in the x column? Then what's the smallest value in the y column? Then what's the smallest value in the z column, right? That's what axis equals 0 does. If you set that to 1, then it checks every single row. All right, what's the smallest one in this row, right? X, y, or z. Then what's this one? X, Y, or z, right? It'll keep going the long way. So we want axis equals 0. We want to find out what is the smallest x value here. What is the smallest y value here? What is the smallest z value here? So that's the min chords. How about max chords? So if I copy this, and I want it to be the max chords instead of the min chords. So let's change this to max. And what do you think I need to do to this to go from min chords to max chords? Hint, it's not a lot, right? It's 2 letters. Max. Now it's going to take the max there. So now I've got 2 vectors. I have one vector that has the smallest x value, the smallest y value, and the smallest z value. The other one has the largest x, the largest y, the largest z. So if I just take the difference between all of these, I can see how much the system spans in the x direction, the y direction, and the z direction. And this will give me an idea of the dimensions of my protein. So these are both vectors, right? They're numpy arrays. We can treat them as vectors. That's one of the many amazing things about numpy arrays. So I just have to take the difference here. Max chords minus min chords. We run that, and there we go. We see that the dimensions of our protein are in the x direction, spans about, a little over 38, almost 39 in the y, and in z about 33 and change. Okay, so that's, call that 40, right? If we had a box that was 40 angstroms by 40 angstroms by 40 angstroms, that would just enclose it. And the ChemCompute people say you should about double it. If you were to put this thing in a box, a really tight box, double that, and then you've got enough water in there. So this was an important step. So when it's time to put this in a water box, remember this for later. We're going to choose a box size of 80 angstroms in all directions. All right, so now is the part where we actually start using ChemCompute. So I've already got ChemCompute open here. And once you've signed up for an account, you should log in. You see there's me, G. Grazioli. I'm logged in. And then I can go to NAMD. And I want to submit a job. So I click Submitting a Job. And the default protein here is ubiquitin. I don't want to do that one. I want to do, what was it again? We have the name in here somewhere. Let's go find it. There it is, 1CSP. 1CSP. So I put the protein data bank name in there, which I think it's so cool that this this connects directly with the protein data bank. So you can just give it its ID number and it'll go pull that, right? So ChemCompute is doing so much stuff for you. It's important to kind of acknowledge what's going on here, right? So ChemCompute, they're giving you a web interface where you can give it a protein data bank ID and it'll go pull the structure and load it in here. This number here, sometimes a structure, like if it's an NMR structure, they actually fit different structures to their spectroscopic data. And oftentimes people will upload maybe 10 structures and say, these were the 10 best fits. So which one do you want? We'll just go with the first one. That's fine. Our box size, we did this, right? We want this at 80. Let's bump that up a little bit. We're going to make that 80. And notice when I increase this, the number of waters increases down here, right? Because our simulation's actually going to have a bunch of little water molecules in the box with the protein. Because again, if there's no water, you're not really simulating a living system very well, or a molecular system from a living system very well, right? The other parameters, we'll leave them the way they are. Run the temperature at 310 Kelvin, that's fine. Don't touch the number of minimization steps. If you want to try and save yourself a little bit of time, like if, particularly if you have like maybe an older laptop and you don't want it to be chugging away on some of this stuff, maybe run for less molecular dynamics steps, right? So the minimization, leave that alone. So basically when you run a molecular dynamics simulation, if you just kind of throw a structure in there and you've put some waters in there and the proteins in there and you haven't been really careful about where the atoms are, you could have you can cause something called an overflow error, right? So if you've got two atoms that are really close together and then you just go ahead and you start your molecular dynamics simulation and they're right next to each other, Well, the simulations is calculating all sorts of forces and energies that are a function of distances. So if they're like right on top of each other, you could produce a force so strong that the object that was created to store that, right, the amount of memory that was allocated to store that information is not enough, and it overflows and it crashes the simulation. So you always have to minimize first. So that's what minimization does, is it just gets your system into a nice low energy state. And then once it's there, then you can start running dynamics. So that's why I said don't touch the number of minimization steps, probably leave that alone. But dynamics, if you want to run less steps, that's totally fine. The time step size, 2 femtoseconds, that's super common. We'll leave all this default. This is just which computer are they going to run it on. An important thing to know about molecular dynamics simulations is you can't really run them on a laptop or something like that, right? These are we call it computationally expensive. It takes a lot of computing power to simulate a molecular system. So because of this, molecular dynamics simulations are always run on remote servers. So we have servers that typically run the Linux operating system and you access them remotely. They run in some server room, right, with lots of cooling and special stable power supplies and things like that. And it's a skill to develop, right? If you end up doing this sort of work in your career, that's the way you'll do it, right? But what they've done at ChemCompute is they've made a really nice, easy interface where all of that stuff happens automatically for you, right? So again, I'm just kind of making it clear what's happening for you. Usually you would move your files to one of these remote computing clusters, and then you'd have to queue it up and run it on there. So you would need to know how to use the Linux command line and things like that. But this way we can do it all through a web interface. And notice down here, you can either have a 1-hour maximum or a 6-hour maximum. And so if you were wondering, like, wait, if there's this great web interface, why do people still learn how to do it with the Linux servers and that sort of thing that I told you? Well, this is why, right? You can only do so much like this, right? There's a cost to anything you do. And they've done an amazing job of setting this up. But if you're going to do this for your research, you're going to need a lot more power than this, right? You're probably going to want to run on a lot more cores and for a lot longer than 6 hours. So this is an amazing tool for learning. But if you decide you really like this stuff, it is definitely worth it to learn how to submit jobs in the traditional sense of working with a Linux terminal. But okay, so that's everything on this interface. Let's hit submit. So there we go. We've been given a job ID. It's been submitted to Jetstream 1 or 2, right? That's the computer that's running it. And these gears, once the gears are turning, then you know your simulation is running. And I ran this one yesterday. I can't remember how long it took to run. I think it was a couple hours. So this does take time. So if a professor assigns this to you, don't start doing it the morning it's due or something like that. This takes time to do it. All right, so now I'm going to do kind of like what they do on the cooking shows, right? Something has to bake for 3 hours and they just cut to the next thing and they've already got it made. I'm going to do that now. So let's say that my ChemCompute simulation finished running and I click download. By the way, your job number here, I forgot to mention this. They assign a job number. You should always kind of write that down or copy it down somewhere because if you need to look it up later, then it'll be easy to find. But okay. So let's say I downloaded my results from ChemCompute. There's a button for doing it. It's very straightforward. It's beautifully laid out, the whole thing. And then when you download it, it's basically your job number.zip, right? So you download that, you get this big file, and then I unzipped it. Right, unzip it like that. But then I renamed it to SimData, like for simulation data, because I'm never going to remember this number, right? So this folder right here is really all this stuff. I just renamed it SimData. So I'll go delete that. So this is all of that stuff. All right. So now let's start taking a look at the data that we produced with that simulation. The first thing we're going to need to do, we're going to want to load all the data from the simulation. So let me uncomment all of this for a moment. And this is sort of partial code. This isn't going to work if you run this, right? It doesn't work. But what this does, we have to give it a path to 2 important files. So if we look in here in our simulation data, and notice my simulation data is here. The Jupyter Notebook that you're seeing open in my browser is here, right? Never forget that your Jupyter Notebook is running on your machine. Just because it's on the browser doesn't mean it's on the internet, right? It's running locally. So this is where that file lives. This is where SimData lives. So if I give a file path to get from here to there, right? This is an important thing to know. So, all right, in SimData, we've got a ton of files in here. And I will tell you the ones that we're going to be using. There's there's a PSF file and there is a DCD file. So PSF is protein structure file. DCD, I think it's dynamic configuration data, something like that. I forget exactly what DCD stands for, but it's basically moving coordinates, right? Dynamic coordinates data, something like that. So boxwb.psf, that's the PSF file we want. And there it is, md.dcd, that is the file that has the coordinates as they change over time. So let's load these things in. So this file is going to be part of this file path. So I'll put that in first, just so I remember what it is. And then the other one was, it was md.dcd, right? I'll just put that from memory. md.dcd. There we go. So this is going to be a file path, right? Operating system, right? We brought in the operating system library, the OS library, and we're going to create a file path. Okay, so the file path starts where this Jupyter Notebook lives. But then I got to go into SimData first, and then I can find this thing. So we got to put SimData first here. So let's put that. There we go. Put SimData. Whoops. SimData. There we go. And now we're going to hit enter, shift enter. We're going to execute that. Looks like I got some kind of warning in here. Oh, okay. It's just a deprecation warning. That's okay. We can ignore that. And next, so we've created a universe, right? So we've created a universe just like we did before, right? Before we created a universe just using a PDB file. Now we've created a second universe, and we're just going to call this one U. Right? So we have a universe called U, and this is the only other universe we're going to create in this session. And while that first universe, it had the position of all the atoms exactly as it is in the protein data bank, this one has a lot more information, right? This is a moving structure, right? That DCD file tells us how the structure moves over time. Okay, so now what are we going to do with this universe that we have? Well, let's take a peek at things. Let's see what it looks like, because remember we looked at one before. And so let's look at, we're going to create an object called wbox. So I put that in there, commented out for you to get you started. And so we're going to call a function. It's as a method built into our NV object, right? This is our object for NGLview, right? So NV is our NGLview, and we say dot show MDAnalysis U. Well, the reason we can do this is that there's been some collaboration, right, between these groups. Maybe it's the same people, I'm not sure. But the MDAnalysis and the NGLview, they can work together. So I'm calling an NGLview function, but I'm passing it an object from MDAnalysis, a universe. And this is the function that allows me to do that. So let's just take a look at that real quick. Let's see what that looks like before doing anything else to it. It's created, and now we can look at it. Oh, there it is. Cool. So here's our structure, and watch, I can hit the play button and this thing moves, right? So we're actually looking at our simulation that ran on ChemCompute. So we got all the data, the DCD file tells us how this thing moves. I can speed it along a little bit, kind of look at how this thing moves when it's just kind of chilling out there in simulated water. All right, but then there's some further instructions. I say like, okay, let's add a representation. I want you to see it with the water molecules there, right? Because you know, it may not look like all that much right here, right? But I want you to see it once with the water molecules there. So what we're going to do, we're going to take this object here. So this is our show MDAnalysis object, and for that we can modify it using the add representation method that's built into this object. So what we're going to do, we can give it a different type of representation, and so I want to give it as what's called licorice, right? Licorice. There it is. So there's licorice, and I want to represent the water molecules using the licorice representation, and I think they call it that because they kind of look like candy. Honestly, specifically, they look like Good and Plenty's. So if you know Good and Plenty's, I think that's why those taste like licorice. I think that's why they call it licorice. I think it's a reference to Good and Plenty. Anyway, let's see, what do we got? Water. Yeah, so this is the representation we want to use. And then you have to tell like, okay, which molecules? Do you want the protein to look like licorice, or do you want the water to look like licorice? So we go selection. And if I just type SEL and then hit tab, it fills it in automatically, right? Because this interactive environment does that for me. And now for the selection, I'm going to say water. So that's a keyword. It knows what I mean. If I say water, it knows to select the water molecules. So it's going to select the water molecules. It's going to represent them as licorice. And then also we have to give it a color. So let's give it the color. I like the color cyan. So cyan is half green, half blue, right? All the pixels on the screen, you got R, G, and B. So if you turn the red pixel, if you turn the red completely off, and then you turn, you could turn the green and the blue all the way up, you get cyan. So this is cyan. So let's take a look at what this looks like now. There we go. So that's that blue-green color. We call that cyan. So here we go. Now we've got the water in there and everything. And wow, let's hit play now. So you see everything that's going on. You see all these water molecules bouncing around, doing their thing. The protein's in there too, right? They're all interacting. I could zoom out, right? I can use like the wheel, like the mouse wheel. Push that up. See, here's our box. Remember we made a box of water? Now you can actually see our box of water in there. So I think this is so cool, especially that we can do it inside of a Jupyter Notebook. I love this. So there it is. So now you've seen it with the water there as well. So let's go on to the next step. All right, so for this next step, we are going to do some analysis of the structure, because it's one thing to kind of look at it and just be like, wow, that's pretty cool, right? But then it's another thing to try and like, be a little more scientific about things and say like, hey, it sure is jiggling around a lot. Then we can ask a question. We could say like, okay, which amino acids are jiggling the most? And then, okay, how do we quantify their jiggliness, right? How are we quantifying how much they're jiggling? Well, one way to do that, we can look at along the backbone, right? So if you trace along the backbone, you're going to run over every alpha carbon, right, of a protein structure. And if you look at how much those alpha carbons are jiggling around, that'll give you a good sense of like, which regions of the protein are pretty rigid, like kind of folded in tight, which are kind of a little more floppy. So we're going to try and see what the wiggly parts are, right? Which parts are jiggling the most. And the particular metric we're going to use is RMSF, root mean squared fluctuations. All right, so root mean squared fluctuations, what does that mean? Well, I want you to read this thing carefully, right? Because I wrote all this stuff for a reason. And there's actually a really good video from the MDAnalysis people. So this is the video. I linked to it in the Jupyter Notebook. So if you click that, it'll open this. And in that particular video, Dr. Beckstein does a really good job of explaining a lot of things you could do with MDAnalysis. I think he's one of the people that built it, right? So obviously he knows what he's talking about. But anyway, there is a section of this video where they calculate root mean squared fluctuation. It's close to here. Let me turn the sound off. And I will just, there, this is the spot. So this particular video, they show you how to do it here. So let's take a quick look at what they did. All right, so they have a universe. They select all the carbon atoms, or sorry, they select all the alpha carbons. So let's do that first. We know we're gonna have to do that. So we're gonna select our carbon atoms. So Ca is gonna be equal to, these are alpha carbons, that's why I call it Ca, right, carbon alpha. U.select atoms name Ca. Let's see if I could do that from memory. U.select atoms, and no, couldn't do it. What was it again? There it is. Name Ca. Name Ca. Okay, so we're saying name. We're saying like the type of atom, the name of the atom is Ca. So if you look at a PDB structure, if we look at this thing, I'm going to open it with a text editor. Text edit. If I open this thing in a text editor, right, when you load a PDB file to read it, this is actually what it looks like. It's text. So if I'm going to look for Ca, and let's find one here. There we go. Done. So you see this right here? Here we go. See, this is a CA. This is the name. So when you say name, I'm saying, okay, I want the name column here. This is the name column, and I want it to be this name, CA. Right? So this is actually a command, right? We pass it as a string because underneath the surface of this, in the back end of this, it's basically parsing this into a command, like, okay, name equals CA, and it's checking for that. Okay, so we've selected the alpha carbons just like they did in the video. And then if we look at how they go through and calculate the means, they have a really nice, concise way of doing it. And this is actually a really smart way to do it. In particularly, it's a smart way to do it if you have to take a mean as you collect data, right? Like, so imagine like maybe you have a really large data set and you can't even fit it in RAM. It's that big, and you're loading it bit by bit, and you're averaging as you load it. That's kind of what's going on here, where they have, I won't spend too much time on this, but notice how like their enumerate here. They do enumerate, and then they get K to get the index. And then they use the index here to reweight as they total things up, right? So the sum of the squares, here they're calculating the sum of the squares, but they multiply it each time by the weight, and it's weighted by like how far along you are in the loop. So if you want to do it exactly as they did it, go for it. There's nothing wrong with that. But there's another way to do it too, right? So if you want to just sort of lift their code and type it in here, that's totally fine. But make sure you take the time to read it and understand what it's doing, right? You don't want to ever run code that you don't know what it is, right? You don't want to just blindly run other people's code, right? And always give them credit too, of course, which I'm doing right now. So yeah, so you could do that. But I thought, let me show you another way to do it too that is maybe a little easier to read. So again, this is actually like a great way to do it, especially given the circumstances I described, but there's kind of a more readable way to do it. So I thought, let me offer another way to do this same calculation. So the first thing I would like to do is let me just get all of the positions into a single array, right? So I know I'm going to make it be a numpy array. Right, so what am I going to take here? Well, actually, let's do that at the end. Let's do list comprehension here. So I want to loop over a trajectory, and so what's really great is that you can do that with u.trajectory. U.trajectory, right? If I hit tab, offers me trajectory. So I can actually loop over each step in a trajectory. And a common way to write the for loop is to go for ts for time step in u.trajectory. Okay, so this list comprehension, I usually teach my students, write this part of the list comprehension first, right? Write the for loop. I want to loop over the time steps in u.trajectory. Okay, what do I want to do with each time step now? So then I go ca.positions, right? Because that'll grab the position. So let me run this, make sure it runs. Okay, it runs okay. And let's take a look at ca positions now. Uh-oh, that's gonna be a lot. Okay, there it goes. So yeah, so we've got XYZ coordinates and we've got all the positions at each time step. There's the first time step, there's the second time step just started. So we've got all of the positions loaded into a list of arrays, right? Because if you notice this thing, right, let's check the type. Type, it's list comprehension, so of course I made a list, but just as a good habit, let's check the type. It's a list, right? So I have a list of arrays, but I really would just want this to be one big array. So I can force this thing to be an array by going np.array. So I'm recasting this as a numpy array. So now I've got a single numpy array that has all of the CA positions in it. And why do I need this again? Well, if I'm trying to get RMSF, right, root mean squared fluctuations, I want to know how these things are fluctuating about in their positions. So now I have all of the position data. So at this point, I need to know what their mean positions are first so that I can figure out how much they're fluctuating about those mean positions, right? So you get the mean positions, and then you can subtract all those positions at each step, and that's a movement away from that mean position, right? And then you can get statistics on that. You can take the mean of how much they're fluctuating away from those mean positions, right? So there's a couple averages going on here. All right, so let's get the mean positions now. So we've got CA positions, and as I mentioned, this thing is an array, right? And of course, NumPy arrays have a ton of built-in functions. So let's go .mean, because yeah, you can take a mean along an array. And similar to before, where we were checking, like we were trying to find the lowest x value, then the lowest y value, then the lowest z value, right? We gave it an axis. So we're going to do the same thing here. We're going to say axis equals 0. So if I do that, now let's see what these mean positions look like. Let's look at that real quick. Cool. So I have a single array, and if I go to the end of this thing, see how long this thing is, right? So if I take the length of this, length of that is, or I guess we could just say shape. Well, that's fine. We'll take the length. So if I look at the length, 67. So are there 67 alpha carbons? Yeah, there are. That's what. So this is the mean. So now we know the mean position of every alpha carbon in the whole structure, right? And thanks to this fantastic library, we've done it in very few lines of code. All right, so now we've got our mean positions. What do we want to do next? Well, now we can start figuring out how much each of these positions are fluctuating about those mean values. All right, well, let's break this down. Root means squared fluctuations. Okay, so we got to get some displacements and square them, right? The fluctuations, that's how much we're moving, how much we're displacing away from the mean, and we got to square that. So let's get our squared displacements. All right, well, as I said, it's displacing away from the mean. So why don't we subtract it from that? So if I go CA positions minus mean positions, right? Let's see what that looks like. Copy, paste that there. There we go. So look at this, I have this set of arrays. So it automatically went through and subtracted the position of each alpha carbon at each time step from the mean position of its respective alpha carbon. All right, so that's the difference. Can we just square it too? Yeah, we can, right? This is the beauty of working with NumPy arrays, is you could just treat them like vectors, matrices, etc. We don't have to like write for loops and loop through these things, right? We'd have to do that in other languages, like maybe C or something like that. But not here. All we have to do is that, and now they're squared. That's it. Now they're squared. So, okay, we've got our squared displacements. Now, what else did I tell you to do? Let's do the mean squared displacements. Okay, we got the squared displacements. We got to take the mean of that. So let's take our squared displacements and go dot mean again, right? We keep using the same trick and it keeps working for us. And so we're going to have to give it an axis again. So we're going to go axis equals, and what do you think? Do you think it's going to be 0 or 1 this time? Yep, 0 again. So if we do that, let's see what this looks like. So I'm going to copy that, paste it there, run it. There we go. So these are our mean squared displacements. Okay, so we see this is just one single array, right? This isn't like an array of arrays or a list of arrays or anything like that, right? These are our mean squared displacements. And you know, when you see plots of RMSF, it's not like a three-dimensional plot, right? You're only seeing like one value of RMSF. And so what happens is you actually have to add x squared plus y squared plus z squared. And you think like, wait a minute, can we really add across these different dimensions? Well, when they're squared, it's different, right? So if you want to think about the unit vectors, right? If you take like 3 times x hat times 4 times x hat, right? So that's 3 times the unit vector x hat and then times 4 times the unit vector x hat. If you multiply those together, the unit vectors, you basically have the dot product of 2 unit vectors, you just get 1, right? So it becomes a scalar. So when you add these together, you're just adding 3 scalars together. So if it kind of freaks you out for a second, like, wait a minute, why are we adding x, y, and z? It's actually, you know, x squared, y squared, and z squared, and the vector component went away. There's just scalars. So if we want to sum that, you guessed it, dot sum. You say dot sum. So now we're going to do our sum. Now this time, are we going to go x equals 0 or x equals 1? If we're summing across x, y, and z, right? So before we were summing, we were doing things vertically, right? When we looked for like the smallest x value, we went down vertically, and then it was axis equals 0. Well, now we're going horizontally. We're adding the x squared, the y squared, and the z squared. That's horizontal. So now x equals 1. So if we run that, all right, now we've got these values for mean squared displacements. All right, so we're super close, right? What are we missing? It's RMSF. We have mean squared displacements. And we've averaged. So this is actually a mean squared fluctuation. That's what we have here. We've got mean squared fluctuation. So we're just missing the r, right? R is a root. Well, we mean a square root. That's why we call it root. So let's just take the square root of this thing and we're good. So now we go numpy dot square root, sqrt, and we pass mean squared displacements. Copy that, paste it there, and we run that. And there we go. Now we've got our RMSF values. And I decided to just give you the plotting commands, right? So these plotting commands, I took that from here. So this is the way they plot it in this video. I thought, that's great. Let's leave that alone. And again, there's nothing wrong with calculating the RMSF this way, right? There's times when this is actually a much better way to do it. But I just think this is a super readable, easier to teach way of doing it. So that's why I opted to do that. But for the plot, I just took their code. So command slash, by the way, this is a good thing to know if you don't know this in Jupyter Notebooks, right? Command slash that can comment or uncomment multiple lines. So I'll uncomment that, run. Uh-oh, what did I miss? Oh, I should have left that a comment. There we go. There it is. Okay, so here we have RMSF as a function of the alpha carbon residue ID. So, just to remind you, residue ID, amino acids are residues. So the res ID is like which amino acid is it going along the backbone. So here we have it, RMSF as a function of residue ID. So there's an obvious one here, like that's the most jiggly one, right? There's no question. That is the most. Second most is probably that one, but it's close between that one and that one maybe. But I'm pretty sure it's that one and that one. So I can eyeball that. And so the next question says like, all right, what are the two most jiggly ones here, right? Which two are fluctuating the hardest here, fluctuating most vigorously? Well, I could, read it off the graph like that. But another way to do it, let's be a little more strategic about this, and let's find a coding solution here. So if we're going to be more principled about this, I could take all of these RMSF values and put them in a pandas data frame with the residue ID. So you have the IDs, and then you have the RMSF values. And then the reason I would put it in a pandas data frame is that there's so many great built-in methods there. And one of them, you can sort the rows based on one of the column values. So that's what we will do. So we're going to go down here. Let's uncomment this. And, whoopsies, let's make a data frame here as I described. So one of the most straightforward ways to build a data frame is to make a dictionary and then pass the dictionary to the data frame. So a dictionary, we need our curly braces. And then of course, dictionaries, you have a key and a value, right? It's a sequence of keys and values. And then when it becomes a pandas data frame, those keys are going to be the column names and the values are going to be filled in as each row of the columns. So we'll do the residue ID, res ID, that'll be the one, and then the other one will be RMSF, RMSF, okay? So let's see, the RMSF, we just called it RMSF, right? So let's put that, that's going to go here. And our residue IDs, well, we can get that from, remember when we did this? We selected all the atoms. So these are only our alpha carbons, right? Because we don't want the res ID for everything. We only want the residue ID for our alpha carbons. So what I could do a CA, where'd it go? There it goes. I can go CA dot residues, right? So, and remember with these objects, you hit tab, start typing it, you hit tab, it'll tell you what your choices are, right? So I can go residues, and then I want the res IDs for the residues. So CA took the residues, and I go res, hit the tab, res IDs, there it is. So if I run this, I have created a pandas data frame. So let's take a look at it. So if I go res ID with RMSD, and I type head, right? This is a built-in method for pandas data frames, so I can take a peek at the first few rows, and we see this. So we've got the res ID, and we've got RMSF. Cool. So the information's there, now I need to sort it. And I recommend that we just sort it in place, right? Because you could make a new copy of your data frame that's like your sorted version, or you could just sort the one you have and overwrite that. And the way to do that is you can go res ID with RMS. Oh, I called it RMSD. Let me change that to RMSF. RMSF. Let's get this correct here, huh? Copy that. Paste, paste. Okay, it's good there. Great. Rerun that. Cool. Okay, so now, so we want to sort. So we got dot sort values. So sort underscore values. And then the column that you want to sort it by, right? Because, you know, we don't want to sort it by res ID, right? We want to sort it by RMSF. So you pass that column name. You say RMSF. And then if I do that, it's going to do this. Okay, so that tells it to do it with RMSF. But remember I said I wanted it to be in place, right? I want to actually sort this object, not like make a copy. So then I have to go in place equals true, right? Because default is false. So if I run that, close, right? But look, it's increasing, right? These numbers are increasing. I want the opposite. I want like the from largest to smallest. So what we have to do then, we have to go ascending equals false, right? Because that's true by default. There we go. So here we go, res ID 37, right? So that's this one that's real high. So that's the real wiggly alpha carbon. So 37 is the super wiggly one, and then followed by these. Because remember the next step, they were kind of close. It was very close, but it was 37. It was one next to it. So let's record that in here. So I'll double click on this to open up the markdown cell. And let's put our values here. So we've got res ID 36 is the most jiggly, and res ID 37 is the second, right? Yeah, 37 is the second most jiggly. No, sorry, I'm wrong. 37, 38, 37, 38. There we go. So, oh my goodness, I made a mess. Here we go. So we've got residue 37 and residue 38. There we go. Now, the thing that that caught me up there, I saw it over here, right? Because Python, the index starts at 0, right? If you want the first thing, it's index 0. But the res ID starts at 1, right? There's no res ID 0. So that's what threw me off here. So they're all off by 1. So be careful. Res ID 37, res ID 38. There it is. These are the two I want. Done. Got that. Okay, so the last thing we want to do, let's do a data visualization. So now that we know which ones are the jiggly ones, what if we do a data visualization, like this? We'll leave the water out this time because it does make things harder to see, but we'll leave the water out this time. And let's make the two most jiggly residues look different from the rest of the structure to kind of highlight them, and we can kind of watch them bop around a little bit. All right, so let's go to this step here. Uncomment that. So we want to use this same command from before, right? We used this before, the nv.show MDAnalysis u. And of course, if we put it down here, we can see it. So if we just run it, it looks like this. So that's like we saw before, right? But right now we want to highlight the residues that are moving the most. So again, we need to use this add representation method, right? So we've created the jiggles object, right? We're calling it jiggles. We made the jiggles object and we want to add a representation to it. So if we're going to add a representation, we have to make our selections again. Remember we did that before. We said, okay, well, what do you want to add? What rendering style do you want it to be? Do you want it to be licorice? What do you want it to look like? So let's start with licorice. Let's see what that looks like. Licorice. So we're going to render it in licorice, but now we have to make our selections again, right? Selection equals. Okay, so now our selection is going to be a little trickier. And remember also, let's put the color in too while we're thinking about it, right? If we go back and look, what do we do? The style of drawing it, select the thing you want to select, and what color is it going to be? So let's go with, I guess we could make it cyan again. Let's go green. Let's make it green this time. So I'm going to put the color equals, let's make it green. Yeah, purple and green will look cool. It's like Incredible Hulk color scheme. Let's see. Okay, so our selection, that's the tricky part. So how do we do our selections? I think this is a good time to look at the manual for MDAnalysis. So let me look it up, Python MDAnalysis They have a really great website actually. So they've got all of their documentation here. And so if I go like a basic example, I think our basic example actually has a selection. Yeah, so here's an example of a selection, right? Protein and backbone. So you can use Boolean statements. If something qualifies as being both protein and backbone at the same time, then it'll select that, right? And remember, this is using and or in the Boolean way. So if you wanted to show, let's say, like if you said like protein and water, you'd probably get nothing, because like what qualifies as being part of the protein and part of the water? Probably none of the atoms, right? So if you wanted to show both, you'd actually say protein or water, right? Because that is actually the correct way to say that. We're sloppy in day-to-day language. We don't do that, but that's actually more accurate, right? That's as far as like, Boolean logic. So my point in showing you this is that you can make selections according to keywords, and you need to know what those keywords are. So let's do one more Google search. Let's say Python MDAnalysis selection keywords, something like that. Let's see what comes up. Selection commands. Here we go. I bet this is good. Let's find some examples. There's like name N. So if it's a nitrogen, I want remember CA, we used name before, right? So the atom name, you can do by atom name. You can do res name, right? So this is the website that can show you how to select all kinds of stuff. And there's a lot of things you could do, right? Another thing, sometimes you want to say what things are not protein, right? So in this case, it'd be like the water, and we probably have some ions in there too, maybe some potassium and chloride ions, something like that. So I wanted to make sure that you are aware of how to find out how to make these different selections, right? Because you might want to try and do some other selection that you didn't see in this tutorial. In fact, we are just barely scratching the surface of what you can do with this. So I happen to know a set of selection rules that's going to work, so I'll type them in. So we've got 37 and protein or 38 and protein, right? So it has to be part of the protein and residue 37 and or part of the protein and residue 38, right? So remember, we don't say and here. If I say and, it'll probably give us nothing, right? Yeah, see how nothing is green? But if you say or, right, because nothing is both residue 38 and 37, right? That's not here. That's not possible. But if I would say, show it to me if it's 37 and protein or if it's 38 and protein, now we get to see it. So there it is. So now we can play it and zoom in and watch it. And so like, this is the most jiggly part of the protein. So we can see it jiggling back and forth there. Speed it up a little. Yeah, we see that as it goes, it does move quite a bit over the course of the simulation, more than the rest do anyway. And so now you can visualize that and you can quantify it as well. All right, folks, so that's the end of this tutorial. I hope you learned something. I hope it was helpful, and I'll see you in the next one.